And we're back with chapter 26. Now it's time for sound. Okay, so chapter 26 starts on page 390. And it starts with the idea that the source of sound is vibrations. So anything moving back and forth fast enough or slow enough will create a longitudinal compression and rarefaction wave. And that vibration is what causes the sound. Now, obviously, you also need a medium to travel through. You need something to compress and rarefy around us. That's air. But it can also work through water or through a solid like a metal that sound can transmit through. So different media are going to transmit sound differently. The general rule of thumb on page 393 is that sound moves faster in more elastic material. So the more rigid something is, the more sound will move. Let me undo that. Okay. So more elastic or more rigid material will lead to sound moving faster. As a general rule of thumb, solids are going to have a greater speed of sound than liquids, which are going to have a greater speed of sound than gases. And the reason for that is because they are more rigid. Solids are going to be more rigid, liquids are going to be a little bit less rigid, well, significantly less rigid, and then gases are even less rigid than that. Okay. So sound is going to move faster in more elastic or more rigid material. Okay. It has to do a lot with the stiffness or the rigidity or the hardness, I guess, of the material. Okay. So we also see that when something is vibrating, in this case, it's a tuning fork that's vibrating, what's causing the sound is that alternation of compression and rarefaction. So compression is when the molecules are really close together. Rarefaction is when they're further away. So pushing together, compression, further away, pulling apart, rarefaction. And that alternation of compression and rarefaction is what gives you a sound wave. Now, in terms of measuring the sound wave from compression to compression would be one wavelength, right? I'm measuring there. Or I could go from the middle of a rarefaction to the middle of a next rarefaction, and that would also be one wavelength. All right. So actually, before we get there, let's talk about sound generally. Since we're talking about vibration, let's give an example. So here I have what do I have? A tuning fork. Another pattern that we notice is that smaller things tend to vibrate faster than larger things. So here I have a variety of different sizes of tuning forks. I have a smaller one. I have a medium, and then I have a really large tuning fork, right? This one's extra long, so long that it's off screen. So if I run through these various sizes, I'm going to switch this one out actually. All right, so let's start with my small one. This should vibrate at 426 vibrations per second, or 426 hertz. If I whack it on the table, hear that high-pitched noise, really obnoxious. And it's vibrating, maybe tough to see, but it is moving back and forth. So small things give a really high-pitched noise. Medium things are going to give a slightly lower pitch noise like this. You can hear that there's that lower pitch there, I hope, through the mic. And then the largest things are going to vibrate the slowest. So we'll try that. And you can hear that it has the lowest one. And then if you look carefully, you can see this one ends up looking fuzzy. It's not that my hand is shaking it. It is actually vibrating back and forth really fast. One other thing that I want to note is that you will see a tremendous difference in how you hear it if the vibration is facing towards you, or if I tilt it and now it's facing side to side. So I'm going to show you where my mic is by putting my mic right in front of the camera, like there. And that way I can show you I am facing the mic or I am not facing the mic and I'll tilt it that way. Okay, so I'm gonna go facing the mic and then not facing the mic. And you can hear, you'll hear it really loudly if it's facing the mic like this, but you won't hear it when it goes that way, or you'll hear it much quieter because the sound wave will be going towards you. Okay. So now it's facing you. Should be much quieter now. Louder, quieter, louder, quieter. And the reason for that is that I'm shifting where the sound waves are going. The sound waves are either going straight into the microphone, or when I tilt it, the sound waves are going side to side, but not into the microphone. They're going out in the two directions away from the mic. So that's another piece with the vibrations. The vibrations send it in a direction, right? Now, obviously, sound also travels in all directions, right? It could go all the way through the room. Even though I'm facing this direction, you could still hear me if you're standing behind me, but it's going to be easier to hear me, especially if I add some direction by, going like this so that I'm only sending my sound in one direction. Cool. All right. So let's go back to chapter 26 and shift forwards to the next section, which is page 393, loudness. So loudness is based on the amplitude of the sound. So the amplitude, remember, is like what we have called the height, but really it's the intensity, the back and forthness of that compression and rarefaction. So if things are harder, compressed, and rarefied, like really compressed and then really rarefied, it's going to be much louder. So loudness is directly proportional to the amplitude squared. So if you square the amplitude, you'll get more intense loudness. Now, that means that we can measure loudness on something called a decibel scale. And for a decibel scale, you'll notice that it increases on like a squared or an exponential rate. So if I go up by 10 decibels, that's actually an increase of 100 times more loudness. So it's going to be a lot more intense as the sound decibels raise. All right. If we go over to forced vibration. Forced vibration is when you make something vibrate at its natural rate. So you can create forced vibration by attaching something to another piece. And by attaching to another piece, you can take a normal sound and then amp it up a little bit. So here I have my normal 256 hertz tuning fork. So it will vibrate at 256 vibrations per second. Here's how that sounds and how loud it is. Pretty good. Nice and noisy. 256. Then over here, I have a 256 hertz tuning fork that has been bolted on to this box. So what's going to happen is this 256 tuning fork is going to be vibrating, but it's also going to be vibrating the surface of this box. It's going to put it into forced vibration. And as it puts it into forced vibration, it will amplify the sound. So it'll make it louder. It'll also run out of energy faster because it's using up that energy over a big surface. So let's take a look at that. Now, if I hold that towards the mic, hopefully you can hear that through the box itself pretty intensely. Let me show that again. There it is. So I'm facing that towards the microphone, and you hear that it goes pretty intense, but it runs out a lot faster. So it goes loud and then it calms down a lot. I can also do this on a larger surface. So I could do it on like a really big desk. So if I take the same idea, and this time I'm going to pop it onto the surface of a student desk. So here we go. There it is. And I'll try it again. Now onto a desk. And I don't know if you can hear that, but the desk itself does a little bit of vibrating, causing the tuning fork to get really loud and then quieter as it spreads that vibration out over the entirety of the desk. So you can use force vibration to amplify a little bit. And that's how guitars work. Acoustic guitars, they put the surface of the guitar itself into forced vibration, and that amplifies the noise. Okay. Then we can talk about the concept of natural frequency. So natural frequency is the idea that every material has a frequency that it will vibrate at the easiest. That's how these tuning forks are made. Smaller things vibrate faster. Larger things vibrate a little bit slower because it's harder to move a big thing back and forth. So if you can find the natural frequency of the object, then it will vibrate at that rate. And different materials are going to have different natural frequencies too. So like steel, the same amount of steel would have a different natural frequency than say the same amount of aluminum. So different materials will have different natural frequencies. Finally, on page 395, actually probably not finally, we get to the idea of resonance. So resonance is the idea that if we push something at its natural frequency, it will vibrate more and more intensely. So a great example of this is a kid on a swing. I have a young daughter named Poppy. She's like 4. She likes going on the swing. And if she's swinging, she wants to be pushed. And so I push her when she comes to the very back of her swing. And I push, and then I wait, and then I push, and then I wait. And every time she gets a little bit higher and higher in her swing because I'm pushing at her natural frequency, right? One push every swing, and I'm pushing right at that same natural frequency. Now, I did an experiment last week where I pushed outside of the natural frequency. So I gave her a push, and then she went back, and then I gave her a push real fast, and she fell off the swing. Cried, terrible, bad experiment. I didn't actually do it. So if you don't push at the natural frequency, then the kid falls off the swing. Then you're not going to end up going higher and higher. If I push when you're still on your backswing, then you're just stopping the person from continuing to swing. So you kind of have to create resonance by pushing at that natural frequency. Another great example of this is the Tacoma Narrows Bridge. So the Tacoma Narrows Bridge was built in Washington, and they built it over the Tacoma Narrows, which is like a river, section of a river. And what happened was that the wind started blowing on the bridge right at the natural frequency. So it created resonance, and the bridge deck started wobbling. Well, because the wind was blowing at the same speed over and over and over again, the bridge started wobbling more and more and more and more. So this was back in like the 1930s, 1940. So it was a 40-mile-an-hour wind. And as the bridge deck just started wobbling more and more and more, eventually it was wobbling so much that it went outside of the bridge's capacity, and the deck crumbled and everything fell off. All the people were off at that point. Nobody was injured. I think some cars were left on there, and the whole bridge collapsed. So everybody was fine. But it was a great reminder that you have to pay attention to natural frequency and resonance. And we actually saw something similar to this, not exactly the same idea, when they replaced the railings on the Golden Gate Bridge in the summer of 2020. So they wanted to get something that was going to be a little bit more aerodynamic. And so they replaced some of the railings, the hand railings on the side of the Golden Gate Bridge. And what ended up happening is it made a super creepy wailing sound because when it blew heavily, it created some natural frequency and some resonance just on those railing pieces. And so it made this horrible wailing noise all the way across San Francisco. Really solid. I'll show you a video. It's outstanding. So the other thing is that now when we design bridges, we put a truss underneath the roadway. So in the Golden Gate Bridge, we have this very intelligently designed truss down here that holds the roadway stable and doesn't allow it to wobble back and forth. So these triangles underneath the bridge make sure that the bridge can't just swing back and forth when the wind blows, because we don't want the Golden Gate Bridge to swing back and forth and fall apart. All right. Now the last thing, beats. So beats is when we have two waves that add together. And when their crests and their troughs match up, it creates a beat. So here's an example with a 12 hertz wave and a 10 hertz wave. The 12 hertz wave, I think I've put 1, 2, 3, 4, 5, 6-ish wavelengths in there. And the 10 hertz wave, I've put 5. So what ends up happening there is there are certain areas where you get destructive interference, where the crest and the troughs end up kind of aligning like that, and they get destructive. And then there's others where they line up perfectly, and because they line up perfectly, you end up getting these really constructive areas. And the way that you can figure out how many beats you're going to get is just take the hertz, take the frequencies of the two waves and subtract them. So in this case, a 12 and a 10, 12 minus 10 gives you 2 beats per second. So if I put a 12 hertz wave and a 10 hertz wave together, I should get 2 beats per second by just subtracting them from each other. So when you're looking for beats, and what beats would sound like is you got this, and then together, they're like, it actually doesn't sound very much like that at all. I'm very bad at making noises, but you know, you get something related to that where you can feel like a thrumming or like an emphasis, and that's the beat part. Okay. Okay. So we're also going to hit some practice problems from chapter 26. They are listed there. Best of luck. And I will look forward to checking through those with you shortly. Enjoy.